Transport Phenomena in Biosystem, Module 10, Shell Energy Balances and Temperature Distribution, Segment 3, Forced Convection. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about shell energy balances and heat conduction with an electrical heat source. In this segment, we will discuss about forced convection. There are two limiting types of heat transport in fluids, forced convection and free convection. The main differences between these two modes of convection are shown in the right figure. Most industrial heat transfer problems are usually put into either one or the other of the two limiting categories. In some problems, however, both effects must be taken into account when mixed convection is considered. In this segment, we consider forced convection in a circular tube, a limiting case of which is simple enough to be solved analytically. A viscous fluid with physical properties assumed constant is in laminar flow in a circular tube of radius r. For Z less than 0, the fluid temperature is uniform at the inlet temperature T1. For Z larger than 0, there is a constant radial heat flux, QR equals to minus Q0 at the wall. Such a situation exists, for example, when a pipe is wrapped uniformly with an electrical heating coil, in which case Q0 is positive. If the pipe is being chilled, the Q0 has to be taken as negative. The first step in solving a forced convection heat transfer problem is the calculation of the velocity profiles in the system, which can be expressed by equation 1017. This parabolic distribution is valid sufficiently far downstream from the inlet that the entrance length has been exceeded. Let's consider heating of a fluid in a laminar flow through a circular tube, showing the annular ring over which the energy balance is made as illustrated in the right figure. In this problem, heat is being transported in both the r and z directions. Therefore, for the energy balance, a washer-shaped system, which is formed by the intersection of an annular region of thickness delta r with a slab of thickness delta z is applied. In this problem, we are dealing with a flowing fluid, and therefore all terms in the energy vector are retained. The last contribution is the rate at which work is done on the fluid within the ring by gravity. The energy balance is obtained by summing all the contributions and equating the sum to 0 and divided by 2 pi delta r delta z to get equation 1018. As the limit of delta r and delta z goes to 0, equation 1018 becomes equation 1019. The expressions for the r and z components of the combined energy flux vector can be expressed by equation 1020 and equation 1021. Substituting these flux expressions into equation 1019 and using the fact that Vz depends only on r gives, after some rearrangement, results to equation 1022. The second bracket is exactly 0, which is the z component term containing the viscosity is the viscous heating, which is neglected in this case. The last term in the first bracket, corresponding to heat conduction in the axial direction, will be omitted, since we know from experience that it is usually small in comparison with the heat convection in the axial direction. Therefore, the equation that needs to be solved is given by equation 1023. For the next segment, we will discuss about free convection. Until then, I am Yusuf from Institut Teknologi Bandung.